Oh.
Steps.
Before we get started, copy it down.
Oh wait, can I use this as notes? Is this gonna be good notes for?
That is for tomorrow's video, so I would save the space on there for that. But you could, I don't think there's a back on it, so yeah, probably use your notebook.
I'm gonna go buy a new.
Yeah, mine's getting
This one's getting. I'm actually struggling to find it. Open pages.
Yeah, me too. I wish I was like a regular human being and just like took like from the front, but like we'll just grab a piece from like a random spot and write on it. That was like no way.
That is not normal, but okay.
Well, but if you have multiple concepts, you need to split them up a little bit.
Well, sure, but it's abnormal to not have any organization.
It's organized in here. This is just extra paper.
That's fine. Start copying. Neither of you are ready.
Good point. I forgot what we were doing. I've been compared to a goldfish sometimes.
Also, you should be able to zoom in on YouTube to see this better if you can't see it very well. But
Write out what quantities you know.
so I put these steps together to hopefully help kind of organize what you'll need to do every time on a related rates problem. I will require all of these steps on my exams. So you should plan on that. And for homework. As for the AP exam, you will not be mandated to draw a picture of the situation, but you will be mandated to write out the quantities you know, write the equation, and differentiate over time. We did all these steps when we did our problems last week on Friday. We would draw a picture, we wrote out what we knew, we made an equation that related the variables, and then we just differentiated and solved for what we wanted to know. So if we went back, there's our picture. We made an equation relating all the variables, we differentiated with respect to time, and then we solved. There are going to be more things that you'll sometimes need to do than simply differentiate and then isolate. We'll probably need to do a lot of converting, or we're going to have to find extra values, or we're going to have to be really clever about this quantity is also equal to this quantity, and then substitute that in. Like, we're going to see some of those kinds of examples today and throughout the rest of the week. So it's not always going to be cut and dry, is what I'm saying. But in general, you'll always take these 4 basic steps. And the last thing is to don't forget your labels. Once we're done, we have to label what sort of units we're talking about at the end of the problem. Okay, now I need to ask myself if we're actually going to do this problem here. Oh yes, this is our thing. Okay. Perfect. Okay, are we good? Can I slide away?
Yeah.
Okay. All right, here's our next example. Number 10 in your textbook, page 254. Find it. Also, something amazing to me is that on AP Classroom, the related rate section is called 4.5, and in our textbook, it's also 4.5.
That's cool.
To me, that's amazing that they line up like that. I'm sure nothing else lines up, but. Okay, what are we doing? Number 10. All right. Let's read it.
A radio transmitter is located 3 miles from a straight section of interstate highway. The truck is traveling away from the transmitter along the highway at a speed of 65 miles per hour. How fast is the distance between the truck and the transmitter increasing when they are 5 miles apart?
Okay, this book's a little old. It's talking about like a radio tower, your cell phone tower. So, okay, it's located 3 miles from a straight section of interstate highway. All right, what's step 1?
Draw a picture.
Let's draw a picture of this. All right, so we have a straight stretch of highway. If you want to be like super creative and like draw an actual road, you do you, man. I'm drawing just a straight line. 3 miles away from the interstate. And make this line longer. All right, so 3 miles from the interstate is a tower. Okay, what else do we know?
The truck is going 65 miles per hour.
Mm-hmm.
And,
Does it matter which direction it's going? Is it going this way? Is it going this way?
it's going, well, it doesn't matter if it's up or down,
Okay, why not?
because it just flips the triangle on its head.
Okay.
But it's not going, it would either be going north or south, not east, and not west, because the road is going north and south.
Okay. So it won't matter if it goes north or south because it flips the triangle. What do you mean? Why doesn't that matter?
I mean, you can still use Pythagorean theorem because the hypotenuse isn't going to change, and it doesn't matter which side is which side because they're just, you can be a squared plus b squared or b squared plus a squared.
Sure. Yes. Right. Yep. The distance between the truck going south or the truck going north and this tower, that hypotenuse distance will be the same. It doesn't matter if it's going north or south. So you can just pick your favorite direction. I'll just pick up because I gave myself more room. Okay.
And we know it's 5 miles away.
We know what's 5 miles away.
The distance between the tower and the truck at the point we're looking for.
How fast is the distance between the truck and the transmitter? Yeah, increasing when they are 5 miles apart. So we know, like, let's say the truck is here. We know that this distance to the tower
It's 5 miles.
at the moment that we care about is 5 miles. Okay. Nice.
Oh, it's a 3, 4, 5.
Good. There you go.
Oh.
So this is gonna be your 4 miles. Aw, cute. All right.
Now
Now what? Do you know anything else? Okay. Let's write out the quantities that we know. This is where even though we have, like, this distance is 3 miles, and we know that this will be 5 at the moment we care about, which means we know that distance will be 4 at the moment we care about. Even though we know those things, it's helpful still to give them variable names, because then it's easier to just build an equation that relates all the parts. So we can just still call this like ABC or ABD or whatever you want to do. I'm going to do ABC this time because it doesn't matter. Okay? All right. We need to write out the quantities we know. What do we know?
A equals 3 miles.
Yep. We know A equals 3.
B equals 4.
Mm-hmm.
C equals 5. Ow.
Plus you.
A prime we don't know, right? C prime we don't know, but B prime is 65 miles per hour. Right?
Okay. So yeah, our B prime. So with related rates, we're always going to choose to use Leibniz notation, but it really is the same as B prime. But we know that the rate of change on the side B there is 65 miles per hour. Okay? All right, so we got that one. But we're going to write dA dt, dC dt.
Oh yeah, I forgot.
We're going to use our Leibniz notation. We can use other notation. It's just better to use Leibniz for related rates. All right. Is this really all we know? What is dC dt in context?
It is what we want to figure out.
It is what we want to figure out, but what does it represent in context?
It's how much B is changed in relation to time. Sorry, yeah.
For DCDT.
Yeah, sorry, C.
So how...
So rate of change, C is changing in relation to the
Yeah.
time.
The rate of change that this distance is changing. Maybe it's growing, maybe it's shrinking. Let's give an intuition. Is it going to be growing or shrinking?
Or as grown, if the 65 miles keeps up. Probably.
Yeah, we'll assume it does. Yeah, so this distance is just going to continue to get longer and longer. So we know ultimately that our dCdt should be a positive number.
Yes.
So at least we know that. Okay. What does dAdt mean in context?
It's constant.
Okay,
It doesn't change.
it's constant.
It's zero.
So there's no change, right? The distance there between the road and the tower is not changing in this situation at all. So the rate of change that the distance of A changes is 0. It doesn't change at all. So we actually know dAdt and that's 0. Okay, so constants in the situations of related rates just go away when you differentiate because the rate of change of constants is 0. All right, we listed out what we knew. That's what we want to find. Step 3.
Put it into a function.
Yeah, let's relate the variables with an equation.
So that would be, well, it would be a squared plus b squared plus c squared. So then you do 2a dA over dt, which is just 0. So then you could change that. Plus 2b dB over dt, which is just 65 later on, equals 2c, which is just dc over dt, and then you can swap out the dB dt for 65, and then you can swap the dA over dt for 0, and that would just leave you with dB times 65, which would leave you whatever it is on that side.
Yeah, so we know that, really, we know that, so this first term, we know is a constant term of 3 squared, right? That one's never going to change. This 3 miles never changes. So if we wanted to, we could even just plug that 3 in right away. And then it's super easy to see. Now when I differentiate, that's just going to go to 0. Or, totally fine, you can write 2a times dA dt, but then you plug in 0 for dA dt, and that term will go to 0. Either way, never floats your boat. Make sense? Okay. So, I'll leave it the way that Jonah said it, which is 100% fine. And now what we need to do is let's just plug in our variables, the things that we know. So we said A was 3, yes, 3, times 0, plus 2, times 4, times 65. 2 times 5, at the moment we care about, times, we don't know dCdt. All right, let's find dCdt.
So it's 52
52,
miles per hour.
yeah, there you go, 52 miles per hour. Don't forget your label. There you go. Not too shabby. So that distance is increasing at an instantaneous rate of change of 52 miles per hour after the truck has gone 4 miles.
How much harder do these get?
They can get harder. We're gonna see some harder ones either today or Wednesday, but
I thought this was.
today we're gonna see a harder one.
Okay.
These are the fairly easy ones so we can get our hands on it. And then we're gonna go, okay, let's take it up a little. This next one's not so bad, but I think this is one more good example to see some more of the pieces. I think we're at example 4. This is number 7, page 254. Okay, number 7.
The width of the rectangle is increasing at a rate of 2 centimeters per second. Its length is increasing at a rate of 3 centimeters per second. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters?
Okay. Alright, you guys give this a go. Get it started on your own.
Draw one picture.
This isn't a triangle.
Yeah. What's the one for the area of the rectangle?
Just length times width.
Yeah. Well, I mean, so just use that. So then just be.
But it's
We're gonna do the same concept. Just plug in variables for L and W, which would equal your area. And it's found D L D.
maybe it's dA dt equals dL dt times dW dt. Is that what you're saying?
Well, if we're trying to find the area rate, then we'd have to take the L dt and times the dW dt for length and width. And then times the.
No, because if you think about it, if like the dL dt is
But it's just the rate of change of the length. So. We don't know. Wait, no, we do know that. Yeah, it's just 5 times
it's 15.
5 times 15.
Oh wait, 5
So
times
it's just
4.
20, it's just 20 centimeters squared.
So if we have Oh wait, no, length is,
Standard is percent total length of the DLDT is equal to 2, and DWDT is equal to 2. We don't know the D,
with this one length, so
the DADT. So then we just plug in.
Okay.
But there's not like, it's not like Pythagorean theorem where we can go,
What's the derivative of the?
yeah, that's where I'm stuck.
Wait, remember when the derivative was just the perimeter function at the last semester? Where the derivative of it was just the second one that was listed. Maybe we just write it out.
Shouldn't the rate of change in the, oh wait, we might be done. The rate of change in the area, isn't it just gonna be the rate of change of the width times the rate of change of the length? We're trying to find dA dt. So we know dl dt.
So what was the equation that you used to relate the variables?
Length times width equals area. So yeah, try dl over dt equals 3 centimeters per second. dw dt equals 2. dA dt is unknown. So what if we
The
do?
issue I'm running into is that when you take,
I think it's 6.
but then it would have to be,
I think that, which would make sense because it's for.
would it? But then would this number here, the L, changing to 0 since it's a constant and changing to the variable? Or would it just,
No, I think it's different because
so the possible answers are either
no, we're
6.
already given the derivatives. We don't need to find the derivatives.
No, I know. Well, you have to find the derivative. You have to find the rate of the dA/dt. Then.
Yeah, I know, but we already have dl and dw, and if we know the length times width equals area, the rate of change in the length and the rate of change in the width, if you multiply those together, the product should be the rate of change in the area. Maybe. That's what I think, but I could be wrong. So then, in that case, it would just be 3 times 2, so then it'd be 6 centimeters squared per second. 6 squared.
But then what do you do with the 20 centimeters squared for the area? Because then we still have to find the dA/dt.
What's?
Remember in the equation.
I don't think that I maybe we didn't even need it.
I'm gonna work it out both ways.
Oh wait, no, this doesn't make sense because
Well, we know it's either 6 or the one that we're working on right now.
I don't know what you're working on. Let me be completely honest.
That's valid.
But it doesn't make sense because if it was just the rate of change of the length, the rate of change of the width, we literally don't even need the length.
Well, it's the same.
Measurement.
It's the same thing either way.
Seriously, it's
Yeah.
just 6.
Yeah, it's literally just 6.
6.
No, it's not 6.
6 centimeters squared. 6 centimeters per second.
6 centimeters
No,
squared.
the label's not the issue.
Oh.
The quantity is incorrect. Then we can talk about the label later. But
Did we do something wrong with the area? What if our equation's wrong?
Our equation is definitely wrong. That's why
you've related the variables correctly. Area equals length times width,
but the
which
rate
is a
of
product.
Yep.
Wait. What if we have to use the product rule instead of implicit? With implicit.
That makes sense. So it'd be, we might as well try it. Wait, so it'd be,
Well, we know it's not 6. What if we can cancel that out of the...
wait, but the product rule is for when you're multiplying It's not when you're multiplying 2 to. Okay, no, it makes sense. That makes sense. So it'd be u prime v plus u v prime. So it'd be, if we make u 5, so it'd be 5 times 2 plus.
But then we also have to put in the DLDT in there too. With each variable.
5 times 2 plus 4 times 3. Does that make sense? So it'd be 22.
But don't we have to put the variable after each, like, thing though? Like when we're doing u prime v plus u v prime, don't we have to put?
You
because
said
we
to
still have
leave the
use-
label out to be it.
We still have implicit differentiation though.
Yeah, I know. So, but the thing that we'd be plugging in is dl dt, but we know dl dt is equal to 3. So we can just substitute those. Instead of having dw dt in there, we could just substitute it with 2.
Yeah.
Because we already given it. But we still haven't used any of the length. We have used the length of width. So this makes sense. I think it's 22.
So let's write out the intermediary steps from where our formula is to 22 and see if we can get that.
Right.
So what's the derivative of a variable to the first power?
0.
A variable to the first power.
The variable.
Be
Right.
1.
Like what's the derivative of x?
1.
1.
Yeah.
So it's just the 1. So when we do implicit differentiation, how do we write that?
Just a 1.
Well, you'd have to.
Why do we write, how about this? Why do we write 1 as the derivative of x?
Because it's the rate of change.
It's the rate of change, right? There's a rate of change on y equals x, which is just 1. The slope is 1 everywhere. So that's why we write 1. So what would be the slope, the rate of change of just a?
Oh, it'd just be 1.
Maybe it does have a slope of 1. But how do we write that with implicit differentiation?
dc over dt, right?
dA over dt.
Sorry, yeah, dA over dt.
So the derivative of a would just be dA dt.
Yeah,
Okay, so then we've got that.
that's what we need to find.
Now we need, that's what we need to find. Now we have product rule for length times width.
So we have dl dt times width plus length times dw dt. And then we can just plug in our numbers, correct?
And do we know enough to find dA dt now?
So we know the rate of change of dl dt is 3 times 4 plus 5 times 2, so 22. So 22 centimeters squared per second.
Right? Good. Good job.
Good idea with the product rule, Jonah. That makes sense.
I understand that.
So this was written there because you might need your rules. Product rule, quotient rule, depending on how you relate the variables.
So triangles, obviously Pythagorean theorem. Rectangles and squares are gonna be product rule for length times width.
Yeah, if it's area, yeah. Because if it was like the perimeter, it's just side plus side plus side plus side, which is all a sum. So the rate of changes of those, you would just add those. The reason we didn't have to use any product or anything is because this is a sum. A plus B equals C. So then we just took the derivative of each term. Here we had the actual product rule. So when you had to differentiate over time, we had to do the product rule. Okay? Good job, you guys got it. You guys are doing great.
So
Also, they were worried about not having you here.
No, we weren't. That's false. Totally not true.
That's a bad box. All right, next one. Number 18. That's
oil's leaking from an no. Not the ducks. We're gonna need so much Dawn dish soap now to clean the ducks.
No.
And that's the
No.
takeaway.
No.
Okay, this is one where it's gonna be a little bit harder, but we got this. Go ahead and keep reading it.
Out loud.
Out loud would be great.
Okay.
Then I know when you're done.
Oil is leaking from an ocean tanker at the rate of 5,000 liters per minute. The leakage results in a circular oil slick. The depth of the oil varies linearly from a maximum of 5 centimeters at the point of leakage to a minimum of 0.5 centimeters at the outside. How fast is the radius of the slick increasing 4 hours after the tanker started leaking? Note, 1 liter equals 1,000 centimeters. What the heck?
I'm confused.
So we have a triangle and a circle.
Let's make a picture of this.
So there's a
Let's
circle.
try to draw a picture of this.
So, wait. We gotta draw a little boat in the center of the circle. Yes.
This is 5 centimeters. This is 0.5 centimeters. So it'll be like a triangle on its side, and then it's a circle.
Okay. So we have a circle. So like we have
It's
in
actually-
the water.
It's actually like a cut down cylinder.
There's our circular spill in the water. Okay. Where's the triangle that you're talking about coming from?
I mean, just from one side to the other.
Okay, what do you mean?
Oh, wait, the oil's coming from the middle.
Yeah. Here's the boat. I drew that.
That can be a good picture.
Oh, it's a
too.
cone! That's what it is. It's a cone.
Is it a cone?
It's a cone.
It's gonna be a cone.
It's gonna be a cone.
I hate cones. I remember how hard these were in geometry.
Wait, what do you mean a cone?
A cone. Think about it. So if you have a circle, and in the middle it's 5 centimeters tall, and on the outside it's 0.5 centimeters tall,
Ew.
it's a cone.
That's lame. I can't use my boat now. I gotta retry. Darn it.
I don't like this.
We got this. So isn't as bad as it seems.
It's worse.
Okay. Super not to scale picture. I'm not an artist. Please don't judge.
My goat is now done.
I don't even remember all the equations for cones.
That's okay. The good news is that we actually won't end up needing it. All right, so we have a rough picture of what's going on here. So at the outermost edge of our oil spill, the depth is 0.5 centimeters. So there's our 0.5 centimeters right there with the water line. And then as the spill goes closer to its leakage point, it's gonna get deeper there as it's, spreading out and getting pushed out in a circular fashion, right? All right, what are we trying to find here?
The water would be under it, not through the middle there. Because the oil would be sitting on top of the water.
Sure. We don't even need the water really,
Yeah.
but
So we're trying to find the area of the slick changing. Oh. Okay.
the area.
How fast the radius of the slick is increasing.
Okay. So we want to find how the radius is changing. Alright, so here's the radius. So we want to find what?
The rate of change in radius.
Yeah, how do we write that?
DRDT.
Yeah, let's use the RDT. Okay, that's our goal. The RDT. Okay, so we're talking about that. What else do we know? Do we know anything else?
The rate is 5,000. Well, I guess the rate is.
The rate of change of the
1,000
area.
Wait.
Yeah, the rate of change of the area is 5,000 liters per minute.
which would be.
So the rate of change of the area is 5,000
The total.
liters per minute? That
Sorry, the
doesn't make
volume.
sense.
The volume.
Okay, the volume, that makes more sense.
Which
So
would
we
be-
know that the volume is changing 5,000 liters per minute. So how about dV dt is 5,000? We know that piece. Okay.
liters.
Yep.
Because then you have to convert it to centimeters squared.
So we will need to convert our liters per minute to centimeters per minute, centimeters cubed per minute, right? So how do we convert that? Well, we can do that while we're talking about it. If I have 5,000 liters, how would they gave us the conversion factor there. What do you
So
think?
it'd be about 5 million centimeters cubed.
Yeah, it'd be 5 million. Because that's 5,000 times, there in the book, 1 liter is 1,000 centimeters. So 1 liter is 1,000 centimeters cubed. Okay. Here we go. So that's where we get that. Okay, so that's 5 million. 1, 2, 3 centimeters cubed per minute. All right, good. All right. So we talked about some of what we know. We drew a picture. Whew. Now what? What do you think?
The radius is going to be expanding.
Okay, so the radius is constantly changing.
No. The maximum height and the 5 centimeters and the 0.5 centimeters are going to stay the same. It's just the radius and the distance between them that's going to change.
Okay. Mm-hmm.
What's its radius right now?
What is this radius right now? I don't know.
So we have to figure that out before we can figure out what it is after 4 hours. What's the equation for a cylinder?
So the equation for a cylinder's volume is 1/3 pi r squared h.
We're gonna use
But what do you notice about our picture here?
Oh, this is pretty easy. This is, yeah, it's just a triangle. So the
Well, we have to imagine this as 3D, right? So this is a cone.
that side length there is going to be 4.5 squared by time the square root of 4.5 squared and radius squared plus radius squared.
Okay. So you're talking about the height. Yeah. Okay. Yep. So we have this cone here that has that height of 4.5 centimeters. How do we account for this part of it though? Is this not part of the volume?
That's a cylinder.
It's a cylinder. Now we have a cone and a cylinder. The volume for a cylinder is pi r squared h. Now let's talk again about what we have here and what we're trying to find and what we know. We know that we're trying to find the rate of change of the radius. We know that the volume is changing with this rate of change. So we need to be able to relate the volume and the radius together with an equation. Trying to think about the next question I want to ask. So the radius is constantly changing, which makes this challenging, right? But even though the radius is changing, that's okay. That's what we're trying to find.
Mm-hmm.
So we just need to be able to relate the radius and the volume together. Let's see. So we have two formulas though for a cylinder and a cone that relate the volume and the radius. But what's another thing that we have in there? In those formulas?
Pi.
Sure, we have pi, but that's a constant, so we don't have to worry about that too much. We have got that height in there, right? Okay, so if we have, I think I'm still on pink. All right, here's your cylinder. We can do it this way, and this will also work. Maybe this will be better to connect the ideas. Let's see. Volume for a cylinder is, here's your formula, it's pi r squared h. Volume for a cone is 1/3 pi, or pi thirds if you prefer, r squared h. Okay. Michael, you were hitting on it. What do we know about the height?
The height is the square root of 4.5 squared plus r squared.
Not 4.5 squared.
It should be. Because you take off the 0.5 and make, I'm just talking about the cone here.
Yeah, okay, so we talk about the cone.
The
What's the height?
the height is just 4.5.
It's just 4.5.
I thought you meant that side length there.
Yeah, so if we plug in 4.5 for h, how would that simplify down with all of those new constants? We have 4.5 here, 1/3, and pi. Can we simplify some of these pieces down? What do we get?
Just plug in 4.5 for h.
Okay. Do it, let's simplify it.
So it'd be 4.5 over 3 times pi r squared.
Can we simplify 4.5 over 3? Might as well.
2.5. 1.5. 3 halves.
Yeah.
3 pi over 2. Yeah. Or 1.5.
This is fine. 1.5 pi r squared. Okay? Alright, let's talk about the cylinder. Side of the cylinder.
Okay.
0.5?
Yeah. So
Alright.
it's just pi r squared over 2.
Sure. I'm gonna write it as a decimal so we can keep the format the same.
Okay.
But you're right. Okay? Good. Alright. What's the total volume of the oil between the cone and the cylinder?
I'll just add those two together.
Let's just add those two together. Okay. Are they like terms?
Yeah.
Yeah, actually we can just combine those. So that's super handy. So the volume of the actual oil is the cylinder and cone together
Is 2 pi r squared.
is 2 pi r squared. Not so scary. Okay, we've got the worst of it over with, really. Just conceptualizing what we're doing.
Mm-hmm.
I've got a cone and a cylinder in this case because the height was 0.5 centimeters. Oh, I still have this cone. Okay, so knowing the formulas, which by the way we'll get into on the AP exam, you don't have to memorize the cone and cylinder formulas. But recognizing what you have and going, oh, okay, I need to add their volumes together. That's like the hardest part of this problem. Okay, so now we have a formula that represents and relates the quantities of the volume and radius for the full situation with the oil. Okay? Now what?
Chain rule.
Chain rule? Okay. What should I write?
1.
1.
Oh, wait.
How about I'll start you with dV/dt. I'll do the easy part.
Equals 1 times dr dt.
DHD.
Okay, how are you getting that?
Well, I mean, your first number is just your height. Or, sorry, your,
No, part of it's 2.
yeah, it's just your height, your first number. Or, yeah,
What's the height?
2.
The 2? No, the height is 5
Oh, sorry.
centimeters total.
What is it?
Okay, your brains are tired, I know. It's fine. I have just one variable over here right now.
Yeah.
2 and pi are actually just constants.
Oh, so it's literally just 2 pi.
So 4 pi, because when I bring that 2 down, I'm going to have 2 times 2 pi. This is power rule.
Oh, because
This
it's
is actually just power rule. Yeah. Times dr dt for the implicit. So we're going to power rule the r, but since we're differentiating with respect to time, we need the dr dt.
Okay.
Okay?
And we want to find dr dt.
We do want to find dr dt. Okay? Great. And specifically, we want to know dr dt 4 hours.
Oh, we
after the tanker started.
we already know dv dt.
Mm-hmm.
5 million.
Just 5 million. We've already done that part. All right.
So dr dt is just 5 million divided by 4 pi.
Okay, but we have r and we have dr dt left. I need to know at least one more of these, either this one or this one, to be able to isolate and solve for the quantity.
Uh-huh.
But ultimately, we are trying to find dr dt, so I kind of need to know what r is.
Yeah.
So how could we find what the radius is 4 hours after the tanker started leaking?
Find the total volume and then
Mm-hmm.
proportionately divided into what? Doesn't make sense.
We need the total volume, what?
After 4 hours, so it's just 5 million times 60 by 4 by so 240.
5 million times 60 times 4, good.
So 5 million times 240.
Okay. What? That clock's slow. Okay, what is this?
That's the volume.
Yeah, but what is it simplified to? What we can simplify this. Earth is like
To a trillion.
Uh,
1.2
it
trillion.
is
Yeah, 1.2 trillion.
1,200,000,000,000.
that's good. That's math. Good job.
Oh, 1.2.
Yeah, 1.2 trillion. Right? No. This is billions, right?
No, that's trillions. Because
Billions, billions, billions. Yeah,
oh, yeah, not trillions.
that's okay. Still good mental math. Okay, so billion, 1.2 billion. Okay, so now we have the total volume after 4 hours, but we also then, why did we do that?
To find the total volume, to find the radius.
To find the radius at 4 hours. So let's calculate the radius.
Radius is equal to the total it's 2 pi r squared. So it's just
divide by 2.
just divide by 2 pi r.
Mm-hmm.
Sorry, 2 pi.
Yeah, just 2 pi, and then you'll have to square it.
Okay, tell me what r equals.
No, do the square root of that.
We have to divide by the 2 pi first. So
Start by dividing by 2 pi.
and then square
Take
it.
square root. Let's finish this. We're so close. We're so close.
That's how
If you could
Ashley
just give us like 2 minutes, because I am recording. Thanks.
43,400.
It's okay.
Sorry about
Can you
that.
close the door?
Oh, yeah.
43,460.07.
It should not be 43,000.
Square root of 8. 2 pi. We should have just divided 1.2 billion divided by 2 pi.
And then take the square root.
So you have like 101,884,955. I think he has it right.
Okay, 1, 2, 0, 0, 0,
Yeah.
2 pi. Take the square root of the answer.
I think you have 1 million. 1, 2, 3.
2 pi.
I can't count the zeros. My eyes are too
No, they're right.
Square root.
I'm not gonna do prior. I wasn't.
We divide by 2 pi, and then you have to square
I wasn't Friday. Oh, were you going on Friday too?
So when I do it, I get 13,880.
it. 13 pounds.
Yeah.
Are you in what degree? What mode are you in?
I'm in radians, but
Oh, you're in radians?
Ooh, do you not
5,
have
6, or 8. Yeah, but 8 zeros. Yeah.
How do you?
Shouldn't matter what mode you're in, but.
Yeah, he did the math.
So if you divide by
I
2, here's the thing. If you don't put parentheses around your 2 pi, it's going to divide by 2 and then multiply that pi. So when you divide by 2, then divide by pi, or put parentheses around your 2 pi, you should get like 19 million or something like that.
Yeah. And then
Square root that.
Okay, we got it.
Alright, so we get 13.
13,819.
Alright, centimeters. Okay, let's finish it. We just needed R. We just needed R to go back here and get R.
So the rate of change of the RDT is 5 million.
Okay.
So now just divide.
He's really stupid, actually. Okay.
Just divide by 4.
Oh, Jordan. Yeah. And he's just supposed to be really fine. He is. Custer got it.
Okay.
Yeah.
We did it, guys.
When he
That's like
comes
one of the
across
hardest
him,
ones.
like,
No way.
he's like, oh, I'm really nice guy.
Because he's back in order.
I feel like people who like
So weird. I opened the door and y'all did not look like
Is it 28?
I trust you.
Point.
He's never had
79.
Yeah, let's do
like,
this
he's
one.
not very social. He's nice.
Oh, well, that's not that weird that he's never had a girlfriend.
No, it's not.
My sister's 20.
There you go.
For, like, the way he's
Okay, so we've got a few more under our belt. We're going to do a few more hard ones on Wednesday. Tomorrow, you